Hi, this is Dr. Dominic White from George Mason University. Welcome to Module 8, our final module in the course. In the videos for this module, we'll be talking about modeling. Your first question might be, what do you mean by modeling and models? Well, the real world is big and messy and complicated. Let's take this classic Aston Martin, for example. It has hundreds, if not thousands, of moving parts. It's big, and of course it's very expensive. But we can create a model of this car, as you see on the right. Now, a toy car is obviously a gross simplification of the real thing, but it also embodies many of the key properties of the original. Just by looking at these two images, we can recognize that they represent the same car. In this module, we're going to learn how to construct mathematical models that are simplified representations of data collected from the real world. Just like Aston Martin's, data can be big and complex, but models allow us to extract meaning from that data. Consider this simple example of two variables, x and y. The 30 data points in this graph appear to be correlated. As x goes up, so does y. We can simplify this relationship between x and y with a simple linear model. In this two-dimensional example, that is just a straight line fitted through the data, and it simplifies our 30 values of x and y down to just two numbers, the slope and the intercept of the linear model. Now, this may not seem very impressive on this simple two-dimensional example, but imagine a dataset with 100 variables and 1,000,000 observations. We simply cannot plot a 100-dimensional graph, nor could we go through all those 1,000,000 observations by hand, but we could fit a linear model to all that data and summarize the relationships in all that information down to just a few parameters. So models can be used to measure the relationship between variables in an existing dataset, similar to the hypothesis testing methods that we used in the last module in inference. However, unlike hypothesis tests, models can also be used to make predictions. You can model data on past stock market fluctuations and predict which stocks will increase in value in the future. You can model how weather patterns have evolved in the past and predict whether or not you should take your umbrella with you when you leave your house tomorrow. Now, even though we can make these predictions, it's important to remember that models are just simplifications of reality and not the real thing. The statistician George Box had a famous saying, "All models are wrong, but some are useful." The linear model that I showed on the previous slide did not go through every point in the dataset. The points lay above and below the line, and it had some error. But it is still useful if we are interested in understanding the relationship between x and y. Think back further to the Aston Martin. The toy car is a useful model if we want to know what the Aston Martin looks like, but it's a terrible model if we want to drive down to the supermarket. The same model can be useful for one purpose and terrible for another. So it's important to think about the end use of our model when we're constructing it. It's also useful to consider whether we are picking an appropriate type of model. The simplifications that models make typically arise because we make assumptions about the underlying data. If our assumptions are not valid, then the model can be very misleading. Imagine if our data was curved rather than linear. We can still fit a linear model to the curved data, but it would be very misleading about the true relationship. The final thing to bear in mind about models is that correlation does not equal causation. What do we mean by this? Well, in the linear model on the previous slide, the variables x and y were correlated. A change in x was reflected by a change in y. Now, even though we would typically think of y as the response variable and x as the explanatory or controlling variable, we cannot say that the change in x is causing the corresponding change in y. This is because we have no way of measuring the direction of the effect. X could be causing a change in y, but conversely, y could be causing the change in x, or there could be a third variable which we haven't even included in our dataset, which is causing the change in both x and y. The linear model doesn't tell us anything about which of these three scenarios is true. It only tells us that variation that we see in x and y is correlated. In the next video, we'll start to look at how we can actually create models in R.